So when we talk about study of objects, like there is an object here. Okay, let's say this is an object, and when the object is if it is, let's say it's falling down a cliff like this. Okay, it may be falling like this, or someone may be throwing it up. So a lot of different things are involved here. So what we do with Newton's laws of motion, firstly, why do we need the Newton's laws of motion? We need this. So for that, you have to understand what is kinematics first. Kinematics, and there is a subject called dynamics. Okay. So when you are studying motion, first thing you will be studying. So this is this is motion. Kinematics and dynamics. Now kinematics is your how the motion behaves. It's the geometry of the motion. So when an object is, let's say, falling down, so it will trace its position versus time. If you take it, first it will move like 2 centimeter, then will move like 4 centimeter. Because why? Because it's accelerating, it's moving. Okay, so there is certain geometry of this motion. Time is like our clock will be counting 1 second, 2 second, 1 1 1 1 1 1. Clock is counting, but your distance is continuously increasing with each passing second. That's why this is a geometry. So when we are not thinking about what is causing motion, why it is accelerating, or that kind of thing, only we are focused on geometry of the thing, then we are talking about kinematics. Okay, so kinematics is basically your x and t. Basically, this is some position of time. X is a function of time. Time passes. So here x increases with time. It is geometrically increasing with time. Okay, so there is a function like this will be here. X of t will be t square. Actually, it is. It's in 1 second it will move one unit. Then in 2 seconds it will move 2 square is 4 unit. Okay, so this is how. So this is the kinematics part. So let's forget about kinematics. First, we will study kinematics definitely. I'll come back to that. And so we are not studying here kinematics. We are not studying here position of this object. You can use both actually. So that is one of the main thing. If you understand motion, the physics of motion, you should be knowing when I'll be using kinematics, when I'll be using dynamics, when I'll be using both. When something is easier, you can solve a problem using both, either this, or you can mix also. So that's why understanding the theory is very much important. Physics understanding is very important. So that is a part of the kinematics. Okay, now in dynamics what happens is we have force also acting. I mean, when we have dynamics, like a particle, we are studying how the motion changes, not geometrically, but other than geometrically, how the motion changes. Geometrically means it's changing in certain way. Okay, it's falling like this, or it's staying at rest. Okay, when it's like executing this kind of simple harmonic motion, there is a geometry as position time geometry. So you are ignoring that now. Okay, here now you see that gravitational force is acting on it. Okay, a particle, an object, a ball is there in the surface, on resting on the surface. When we are kicking the ball, what happens? We're applying a force to it, so it moves, it accelerates. Okay, we are causing. So what is causing the motion? The force is causing the motion. Now let's say like we have a object resting here. Okay, now when you are applying, so it is at rest right now. Even this is physics right now. It says that, okay, there is no force, so the particle should be at rest. So certain geometric information is here right now, like x of t, if we say, is what? Constant. Position is constant. Let's say we have something where the x is here. So it's, let's say it's 5 minus 5 meter. Okay, so the particle is resting at -5. Even this is geometric information of the motion. The particle is not moving. This is the geometric information. Okay, now dynamics, in dynamics what we can say? We can say that the particle is at rest. This is one of the term that you will find, rest. Okay. Then this is like this. Now imagine this object is far away from Earth. So there is another object which is far away from Earth, far away from anything. It is just moving. Okay. Imagine I've thrown a ball towards the star and it has escaped the atmosphere and everything, and it is continuously moving there. So it will continue to move, this object. This object will continue to move. How it will move? It will move uniformly at pace, like this. It's not accelerating. Constantly moving. It is at peace and it is moving towards the star. There is nothing to affect it. Let's say that there is no gravitational force acting on it. Okay, because it's very far away from the star, so you can't even consider the gravitational force of the star here. So it is moving, okay, constantly. This and this. So this is what? This is the state of uniform motion. I told you the object is at peace. Here also it is at rest, it is at peace. It's a Zen state. And there also, when it is moving, it is at peace, constantly moving. 2 meters, 2 meters in 1 second, 2 meters in 1 second, 2 meters in 1 second. Means what? 2 meters per second it is moving, constant velocity. So uniform velocity, rest. These are two important states when we are talking about. We can here also we can have kinematic description of the motion, like x of t. I told you is 2 meters per second. This is the uniform velocity here, distance by time. This is x. Here x of t is, let's say, -5 meters. Okay, so forget about the, I'm just telling you to complete it, but we are not focused on x of t, just simply the geometric, the functional relationship between x and t. We are not doing that. Okay, so uniform motion, rest. So you can see here already the thing when there is no force at all. Let everything be on, like, be at peace in the universe. There is no force. So Newton's first law says that an object at rest will continue to be at rest. An object in uniform motion will continue to move uniformly, or the velocity. So these are two different things. Okay. Now, geometrically speaking, you can say that this x of t is a not a function. X is not a function of t here. Here you can say that x is a function of t. Why? Because the position is changing with time uniformly. So it is a x is equal to what? X is equal to your 2 meters per second it is moving. So 2t, we can say. Okay. So this actually, the speed is x by 2 is 2. X by t is 2. So here actually x of t is this 2t. I might have made a mistake before. So x is equals to 2t. Here x is equals to constant. So you can see that these two are like different descriptions of motion here. I mean, different equations we have. So we cannot, kinematics, if we are considered, we can say that, okay, velocity is like x by t is constant. This will hold here also, this will hold here also. That is fine. That is kinematic way of saying the uniform motion. Okay. So here what happens is, how you can unify these two cases. You can talk about velocity, and you can say that these two are the same thing. Okay. In kinematics also, if you see x of t is equals to -5, let's say. Okay. Here you say x of t is equals to 2t. So what can you say? This is like how the position is changing. Position is not changing. So you say that dx by dt is equals to 0. Here dx by dt is equals to 2. Okay. So velocity is 2 here. Velocity is 0 here. So this is one way to actually say it in one statement, that when there is no force, velocity of the particle is constant, which is same as velocity is uniform. So when there is no force, particle continues to have its own uniform velocity. If it was at rest, it stays at rest. That's how it is going to maintain its uniform velocity. So Newton's first law is nothing but constancy of velocity. Constancy of velocity. When there is no force, force is not there, velocity must be constant. Velocity is constant mean what? Constant velocity is nothing else but uniform velocity. We say uniform velocity. Okay. So this actually encodes two of the statements. So when we are speaking in words, we can say that if it is at rest, it stays at rest. If it is in uniform motion, it stays in uniform motion. But mathematically or even physically speaking, physical quantities, velocity. Okay. So we can just directly say that mathematical statement. If you want to mention what is the mathematical statement, dx by dt is constant when there is no force. Okay. So this is Newton's first law. You can say like this, and when it is actually in uniform motion, even delta x by delta t is also same. Okay. This is also same. This is also like saying velocity is constant. Okay, this is one. And when you are saying it in words, you say that the particle is at rest, stays at rest. Particle is in motion, continues to be in motion when there is no force. There is no force. Now, what is force? You may ask. Force is any interaction that you do to the particle. When an apple is falling down, it is interacting with the earth because of the gravitational force. Okay, so interaction. Force is actually push or pull. In very simple terms, we push something, we pull something. So when there is no push or pull, things will be at peace. This is your first law. So I hope it is very clear, and you are also understanding the dynamics versus kinematics here. Okay, so this is the dynamical law. So these are called Newton's laws of motion. We say it, but this is Newtonian dynamics. Okay, Newtonian dynamics is what? The three laws of Newton. Okay, three laws of motion. That is Newtonian dynamics. Similarly, we have different dynamics also. We have Lagrangian dynamics. We have Hamiltonian dynamics. Okay, so these are all classical dynamics. After this, you are going to have quantum. Most importantly, you have relativistic dynamics. That is there also. So these are relating your force to motion. When there is no force, also we are saying, okay, when there is no force, also that is a relationship between force and motion. We are saying that there is no force, so motion should be like this. Okay, so force and motion, within that we have dynamics to connect it. Okay, so we just study the Newtonian dynamics first. Later in advanced classes, we are going to study Lagrangian dynamics, Hamiltonian dynamics, and relativistic dynamics. So E equals to mc square, that is the consequence of relativistic dynamics. Same thing, force and motion relationship. From that, we are going to derive the E equals to mc square. Okay, so this is the thing. And kinematics, you have kinematics is the geometric description. We can have different dynamics, but kinematics is like, okay. So this is the first law, and then there is the second law. Okay, let's say we do the second law. This is the most important thing because the Newtonian dynamics actually is contained in the second law. Second law is the first is kind of a definition. It is the definition of motion, that there exists uniform motion. I mean, when we are talking about change of motion, we need to first define that there is a constant motion. Once we have the constant motion, then we say that that constant motion of the particle may change. The motion may change of the particle. So that change actually is calculated using the second law. So that's why, okay, let's say for example, like we are defining money first. $10, $20, $30. We are defining. So that is just a definition. Then we say that if you invest the $20, then you are going to get it $20. After 1 year, you're going to get 30. After 2 years, you are going to get 60. Like that change thing. So that is actually the main thing. The first one is the definition. We say that $10 is what? It buys certain amount of gold. So that is $10. Okay, the gold equivalent. We just established that one thing. So uniform velocity was the definition. From the first, we deduce that. What is motion? At the most basic level, it is uniform motion when things are at peace. Okay. Now, the dynamics, how the motion changes with force. That is coming from the second law. Okay. Now, in the second law, what happens? We say, so we have defined uniform velocity. Okay. So we saw that the particle may be at rest, or I have shot the particle towards the star and it's moving uniformly. Okay. So this particle is moving uniformly in space. It is not being pushed or pulled by anything. No gravitational force, nothing. Okay. Now we have this. So we can say that V is constant by first law, no force. Okay. V is 0 here. V is some value 2 meter per second here. Now this is the premise of the first law. Okay. In the first law now, let's say we are applying a force. Okay. we are applying a force in this direction, let's say, or we are applying a force, it is moving like this, we are applying a force in the opposite direction. What happens? How does the object respond? That is the second law of motion. Okay, the second law of motion states that mathematically F is equals to dp by dt. Okay, force is proportional to the rate of change of momentum of the object, and that actually force is a vector. So you have actually, when you are stating the law, you have one magnitude and you are talking about one direction. Magnitude is rate of change of momentum, and direction is, it always acts opposite to the, it is along the direction of the increase in momentum. Like when the particle is at rest, okay, now I'm applying force from the bottom towards up, towards the sky. Now the momentum of the object will change in which direction? It will go up. Okay, so force's direction is the change of momentum's change direction. The direction aspect is there, and magnitude is what? Rate of change, time rate of change of momentum. So this is your second law of motion. So it's easy, right? Force is proportional to the rate of change. Force acting on an object is proportional to the rate of change of the momentum of the object, and it acts along the direction of the increase, the force. This is the applied force we are talking about. But there is also a reactive force also. Applied force, reactive force. Now, reactive force direction would be opposite to the rate of change of momentum. When I'm pushing the ball up, the ball also is pushing me down with a reactive force. Okay, that is the third law. So when it is pushing down, that direction is against it. Okay, against the direction of change, because that force is trying to stop it. My force is trying to increase the velocity. So it's increasing in the direction of the ball. Okay, the reaction force is trying to do, that is a separate thing. Okay, so this is magnitude and direction. Okay, now this is it, and this is the concept behind the Newton's second law. And why this is actually most important? Why? Because we can derive the first law from this. First law is a special case of this one. When, let's say, like F is equals to dp by dt, when rate of change of momentum is constant. Now momentum is what? Momentum is mass times velocity, m dx by dt, or p equals to mb. Okay, in some other video we'll talk about instantaneously d by dt things and those things, delta things. Okay, so here you can, by, if velocity is constant, this reduces to Newton's first law. Okay, so that is why the second law is most important, and third law is there. Now this completely, let's see, dynamics, this completely describes the motion of the, let's say the apple is sitting on the ground and I'm punching it from the bottom, trying to throw it up. Okay, so my force is acting on the apple. Okay, now this second law is going to completely explain what happens to the apple if my force is, let's say, 10 Newton I am applying from the bottom. Okay, so I can completely describe the motion of the apple from my hand, or the force, applied force. This also produces the first law and this. So this is actually self-contained. The third law is additional thing. Additional in the sense we say that, okay, so what happens to my hand? But often in mechanics, like in motion, we are studying only one subject. But we may ask, like, what happens to the person who is doing it? That is of secondary importance. So there comes the third law. So that is why it is also not as important. First and third are not as important. Why? Because of this. We are studying about the motion of the, like, pendulum. We are studying about the motion of the pendulum. We are not interested about what happens to the earth because of that. Okay. Now I'm launching a rocket from here. Okay. I'm launching a rocket from earth. What happens is the earth is also pushed back, but we are not interested. Like it may be moving some millimeters or some centimeters based on, but are we interested in motion of the earth? We are not interested. We are interested in the motion of the pendulum, motion of the rocket. Okay. Motion of the apple. We are not interested in the earth moving towards the apple, but it does move because of the third law. So that is, to have the complete understanding of the system plus surrounding, we need the third law. Okay, because it will be easier sometimes. I mean, it will be needed actually in analysis sometimes. to have the complete information of the universe. So it talks about the universe. These two systems, these two laws, we're talking about the system. Now this comes to the universe. So that is the third law, and it's very simple. Third law is something, this F1 is equals to like, you may have a vector relation. The magnitude of the two forces are equal and they are opposite to each other. Okay. So minus of F2, we can say that. So what? F1 plus F2 is 0. Now here is a very important concept to be had about the third law. That is, if the action and reaction are equal and opposite, isn't net force 0? Someone may ask. But the thing is, when the rocket is moving up, Earth is being pushed down. Okay. So what happens? Now you can see that the forces are acting on different objects. We are not saying that the action and reaction are both acting on the rocket. If both the forces were F1 and F2 were acting on the rocket, then the rocket will not move. It is like what? It's like you have an apple and gravity is pulling down and you are trying to, let's say one object is there, two people are trying to pull it, equal force on both sides. The object is not going to move. But here, how then the rocket is moving if the third law holds? The key is that the force is not acting on one object. I told you, we are not talking about the single object in the third law. We are talking about the universe. Okay. In the universe, so the Earth exerts a force, let's say 30 giganewton thrust. Okay. 30 newton. The rocket is pushing the Earth with 30 giganewton in the opposite direction. Okay. So these 30 giganewton, the canceling, the opposing, they are not acting on any single object. That's why we have motion. Motion is happening. Interaction is happening. This is what interaction is happening. Okay. Motion. So this is third law. So what is the statement of the third law? Every action has an equal and opposite reaction. Now what is action? Surrounding acting on the object or the system. Action on the system, reaction received from the system. Okay, so both action and reaction are not acting on the system. When we are talking about action and reaction, we are talking about the universe. Okay, this is the conceptual framework of Newton's laws of motion. I have explained you the premise, geometric, dynamics. Then I explained you how the first law is serving as a definition, base level. Then we are talking about the change in the base level, which is the second law. Then I talked that second law is the most important. That is the classical dynamics. That is the Newton's law. When you're talking about Newton's law, it refers to Newton's second law. Why? Because of this. Second is a subset of corollary of the first is corollary of the second. Not rigorously, but yeah, I'm telling you. Okay. Yeah. Then what? Third law is of tertiary importance. But it is nevertheless, it is important. Okay. But it is not important for the study of motion of a single object. It is useful to analyze things in a universal setting as a universe. So this, and we talked about how dynamics, where is the place of dynamics, where is the place of kinematics, and this is Newtonian dynamics, Newtonian dynamics. And then we have higher dynamics, like other Lagrangian dynamics, and yet other. This is an exciting field. And then, so this is it. Okay, so I hope you liked it. If there is any comment and any concern, then please let me know.